Hello everyone. Today we are going to understand the Fibonacci sequence or the Fibonacci series along with its code and the time complexity calculation. So let's first understand what the Fibonacci series is. It is 0, 1, 1, 2, 3, 5, 8. So how this series is happening, let's see. If you see any term in this series is sum of its previous two terms. For example, this 1 is coming because 0 plus 1 is 1. Similarly, this 2 is sum of last two terms. 1 plus 1 equals to 2. Similarly, 1 plus 2 equals to 3. 2 plus 3 equals 5. 3 plus 5 equals 8. 5 plus 8 equals 13. 13 plus 8 equals 21, and so on. You can make up to n terms. But the first two terms, which is the 0th term and the first term, they are the constant term 0 and 1. For that, you don't have to do any calculation. They are the fixed numbers. Okay. So if I have to write the formula of this series, that would be Fn is equals to Fn minus 1 plus Fn minus 2 for any value of n greater than 1, and otherwise Fn is equals to n. It means if the value of n is equals to 0, Fn will be 0. If the value of n equals to 1, then it will be 1. Otherwise, it is the sum of last two terms. As it is very clear that this equation can be written in the form of itself, but with a smaller sub problem, right? So it means this problem can be easily solved with the recursion, because this function is calling itself. Fn is calling itself Fn minus 1 plus Fn minus 2. So this is a recursive algorithm, and again this is the base case, right? When at some point you should stop the recursion. So this is the base case. I will write its code in Java. You can use any language of your choice. So we will write the code, write the function public static, let's say fib. This is going to be a recursive function. What is going to be its parameter? Int n. So what is the question? Question is that you will be asked that calculate its, let's say, 10th term. Okay, 0, 1, this is the second term, this is the third term, this is the fourth term, fifth term, sixth term, 7th, 8th, and in the question you can be asked to calculate any term. Okay, n represents that term. Now as we see, it is very simple. Fib n minus 1 plus fib n minus 2. You just call the same function but with n as n minus 1 and n as n minus 2. And every recursive function should have a base case, right? And that if n is equals to 0 or n equals to 1, then simply return n. Okay, otherwise just return its sum. Now let's calculate it. Now let's try it out. Let's say I want to calculate the 6th term. Okay, and int a, and then I will print this a. Okay, 6th term in Fibonacci sequence is equals to a. Let's run it. It comes out to be 8, and if you see here, the 6th term is actually 8. So this function is absolutely fine. Now let's calculate the time complexity of this function. How many operations are actually happening here? There are two operations. One is this and another is this. Two comparison, right? And then you are doing one addition, and along with that you are doing the calling this function for n minus 1 and n minus 2. So Tn going to be 2 plus 1, 3 operation, 3 basic operations. Along with that, we are calling this function Tn minus 1, Tn minus 2. So how to solve this equation? It's not a simple process. We have to create the recursion tree for that. So to calculate Tn, I have to calculate Tn minus 1 and n minus 2. Let's take the example of n is equals to 5. So you have to solve this Fibonacci function for f4 and f3, right? If you break it further down, f4 will be f3 and f2, and f3 will be f2 and f1. And if we break it further down, f3 will be f2 and f1. f2 will be f1 and f0. f2 will be f1 and f0. f1 as I told you, that is the base case. For that you can directly substitute it with answer which is equals to 1. Similarly here, these are also base scenarios. This is also a base scenario. This is also a base scenario. This is also a base scenario. f2 we have to again break it further down, f1 and f0. So if you calculate how much work you are actually doing at each step, if you see how much work you are doing here you are doing 3 operation, 2 plus 1 3, right? Rest of the work is passed down. So 3 operations are happening here, and if you come at this stage, this function will also do the 3 operations. This function will also do the 3 operations. Similarly, if you come here, this function will also do 3 operation. This function will also do 3 operation. This will also do 3. This will also do 3. So if you generalize this, so if you come down, there will be a point where you will reach the base case. But if you generalize this case, here you have only one piece. Here you have 2, n minus 1 and n minus 2. Here you have 4 calculation, f3, f2, f2, f1. So 4. At first level you have 1 calculation, 1 node. At second level you have 2 nodes. At the third level you will have 4 nodes. At next level, if you see 1, 2, 3, 4, 5, 6. Here if you take some bigger example for n is equals to 6 or 7, there will be 2 more nodes. So 8. And if you expand it further, that will be 16 until you reach the base case. Okay. And how? So for every node, you have to actually do 3 operations. Okay. 3 operation we can maybe call it O1. O1 means constant time complexity, or maybe for time now you can call it 3 operation also. So 3 operation, and here it is 3 into 2 operation. Here there are 4 total nodes, and each node is actually doing 3 operation. So 3 multiplied by 4, and at the next level it is 8 nodes. Each node is actually performing 3 operations. So 3 multiplied by 8. I can take this 3 common. It will become 1 plus 2 plus 4 plus 8 plus 16 plus up to so on. And if you see, this is the GP series, geometric progression series, where A is equals to 1, the first term is equals to 1, and the common ratio multiplication factor is 2. 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, 4 multiplied by 2 is 8. So this is the form of the GP geometric progression, AR square. Okay, and the sum of first, and if you see the last term in this series will be 2 raised to power n minus 1, right? The first term is equals to 2 raised to power 0 at the first level. At the next level it is 2 raised to power 1. At next level it is 2 raised to power 2. At the next level it is 2 raised to power 3. And at the nth level, that will be 2 raised to power n minus 1, because at first level it is 2 raised to power 0 actually. At the second level it is 2 raised to power 1. So if there are total n levels, it is going to be 2 raised to power n minus 1. So there are total n levels. So the sum of first n terms in the GP series is A r raised to power n minus 1 r minus 1. Here A is 1, r is actually 2, and number of terms are, how many terms are actually there? There are n terms, right? If you see 1 plus 2 plus 4, terms means levels. So 2 raised to power n minus 1, and 2 minus 1 is going to be 1. So it comes out to be 2 raised to power n minus 1. And obviously there is a multiplication factor of 3. When we try to write it in the form of big O notation, we can ignore the constant term. So we can ignore this 3, and we can also ignore the lower order terms. So it comes out to be big O of 2 raised to power n. Okay. So the time complexity of this Fibonacci series is 2 raised to power n. Could you imagine that this cute looking code and this so innocent code could have such a dangerous time complexity? 2 raised to power n is a very high complexity. It's a very bad complexity actually. Okay? So in the next session, we are going to improve the time complexity of this code. So see you in the next class. Thank you for watching the video. Bye bye. Take care.